Hello and welcome. In this video, we're going to talk about how to solve an exponential equation, how to solve a logarithmic equation, and we're going to tie transformations back to how they show up or how they appear in a logarithmic function. So let's go ahead and jump right in. So let's start with exponential equations. An exponential equation is an equation in which the variable occurs as an exponent. So we dealt with exponential functions. Now we're going to talk about what happens if it's actually an equation, meaning it's not equal to f of x. We're not talking about graphing it. We're saying what happens if some exponential expression is equal to something else. And if it's possible to write the bases in the same way, then it's really straightforward to solve because we can just set the exponents equal to each other. So if 3 to the power of x is equal to 3 to the power of 5, then x has to be 5, right? In order for these two things to be identical, 5 needs to be in the spot where x is. So the first thing we want to try and do when we're solving an exponential equation is see if it's possible for us to rewrite both sides of the equation as a number with the same base, so as an exponential expression that has the same base. That will allow us to simply set the exponents equal to each other. So if we look at example A down here, 27 and 1/3, those are our bases. So I want to ask myself if it's possible to rewrite 27 and rewrite 1/3 as some number that has the same base. Well, I know that 27 is 3 to the third, and I'm going to just put parentheses 3x, and I know that 1/3 is 1 over 3, which means I could rewrite that as 3 to the negative first power. And let's simplify this a little bit. 3 to the 3x, 3 to the 3 to the x, we multiply those two exponents to get 9x. This is going to equal 3 to the power of negative 1. So now that we have the same bases, we could, in theory, take the log of both sides so that we can solve for what exponents are the same. We actually don't really need to show that step, though, because if these are going to be equal, all we need to do is say 9x is going to equal negative 1. To solve for x, we're going to divide by 9. So x is going to be 1 over 9. And just like we learned before, we could actually check our answers to make sure that this is true. So 27... I'm going to come up here, check. 27, 3 times negative 1/9. That's the same thing as 27 to the negative 1/3. 27 to the 1/3, the cube root of 27 is 3, so this is 3 to the negative first, which is 1/3. So we know that we're right. So if possible, always start by rewriting the bases as the same number. But if you look at example B, you're going to notice there's not a way that I can think of that I can rewrite 5 and 16 as something with the same base. If it was 4 and 16, if it was 2 and 16, I'd see some options there, but 5 and 16, they're not. 5 is prime, and that's going to make it a lot harder to try and figure out how to rewrite this. So what happens if we can't rewrite using the same base? If we can't rewrite using the same base, then we're really not going to be able to get to a place where we can set the two exponents equal to each other. What that means is my first goal is to get the variable that I'm trying to isolate out of the exponent. And as we learned in the last lesson, in order to get a variable out of an exponent, we need to take the log of both sides. The base that we're going to choose for our log is going to be whatever the base of our exponential expression is. So we're going to take log base 5 of both sides. Here, that's going to give me log base 5 of 5 to the x, and over here, that's going to give me log base 5 of 16. Now, in the previous lesson, or maybe 2 lessons ago, we talked about how this simplifies to just be x. But in case you've forgotten that, I want to show you how we can use last lesson to actually see that a little bit better. So I'm going to take this exponent, I'm going to drop it in front. This is x times log base 5 of 5 based on the properties of logs, log base 5 of 16. Now I can see log base 5 of 5. Well, 5 to what power is 5? That's going to be 1. So x is going to equal log base 5 of 16. Now, depending on the way that the directions are written, we are done here, right? We've isolated x. This expression is some number that we could find. How do we find that number? Let's just recap what we learned in the last video. We can use the change of base formula, log of 16 over log of 5. If we don't have a calculator, then this is how we're going to leave that final answer. If we do have a calculator, then we're going to approximate our answer using a calculator by doing log of 16 divided by log of 5. And if you grab your calculator and try that, that should give you 1.723. So really, when you're starting these problems, I want you to first ask yourself, can I rewrite the bases to be the same thing? If not, let's get the variable out of the exponent. So we're going to take log base of whatever the exponent is of both sides. Then we're going to use properties of logs to simplify and solve for the variable. If we have a calculator, we can actually plug in the change of base formula on the calculator to get a numerical answer, a rounded answer. If we don't have a calculator, we're just going to leave it in the change of base form. So let's test out some more examples together. Okay, I want you to look at all 4 of these examples for just a minute and ask yourself that question. Can I rewrite both sides to have the same base? If not, what does that mean I have to do? So go ahead and pause the video and think through those questions. Just for each of these 4 examples, don't work through the whole solving, just ask yourself that question, can I write both sides of the equation with the same base? All right, hopefully you had time to ask yourself that question. Number 1, we can, in fact, rewrite them both as the same base. They can both be rewritten as 10 to the power of something, and we'll come back to that in just a minute. On number 2, we can't. 2 and 7 are not going to be able to be rewritten with the same base, so we're going to have to start both of these problems by taking log base 2 of both sides. For number 3, 81 and 9, those can both be rewritten as 9 with 9 in their base. And again, we're going to come back to that part. But number 4 cannot. So we're going to start by taking log base 3 of both sides. All right, I'm going to work through 1 and 2 with you, and then I'm going to have you try 3 and 4 on your own. So how do I rewrite 100 to the power of x as 10 to the power of something? Well, 10 squared is 100, and there was already an x there, so I'm going to write this as 10 to the 2x. 10 from 1/10 means that I need to, I'm going to do this in red, means that I need to change the sign, or I need to reciprocate, which means I need to put 10 to the power of -1. This is going to be times x minus 3. So let me just clean this up a little bit. 10 to the 2x is going to equal 10. I'm going to distribute that negative sign, so negative x plus 3. Now the bases are the same, so we can set the exponents equal to each other, or you could think about that as taking log base 10 of both sides, which will bring those exponents down. And now we can solve. I'm going to add x to both sides. I'm going to divide by 3, so I'm going to get that x is equal to 1. I can check that this works just for my own understanding. 100 to the first power should equal 10 to the negative second power. Sorry, 1/10 to the negative second power. And that's true. 100 is going to equal 100. For number 2, we're going to take log base 2 of both sides so that the exponent can come out. So log base 2 of 2 to the x is going to equal log base 2 of 7. So taking the log of both sides is the same thing, the same idea as like squaring both sides, or raising both sides to the power of 2, or multiplying both sides by 2. Log is just an operation. We're taking the log base 2 of both sides. So I can drop this exponent in front. So this is going to be x times log base 2 of 2 is equal to log base 2 of 7. Log base 2 of 2 is 1. So x is equal to log base 2 of 7, and I'm going to go ahead and do the change of base formula here. Again, if you don't have a calculator, that's going to be your final answer. If you do have a calculator, we're going to get an approximation, which I encourage you to try out on your calculator. Okay, go ahead and pause the video and work through numbers 3 and 4 on your own, and then unpause the video and see how you did. So hopefully you've had time to work through those 2 problems, and you've gotten here. So 81 can be rewritten as 9 squared, so 9 to the 2x. 1/9 can be rewritten as 9 to the negative first. Check and make sure that you distributed that exponent, or distributed that -1 to the rest of the exponent, so we get 2x is negative x minus 3, and when we solve that, we get that x equals 1. And we can plug that back in to confirm 81 to the negative first power is 1 over 81. 1/9 squared is 1 over 81, so we do in fact get the same thing on both sides. For number 3, we're log basing 3 both sides. We can drop this exponent in front, so we end up getting x is log base 3 of 8, which we can use the change of base formula for. And just in case you did grab your calculator to practice, this should be 1.893 if you evaluate it on a calculator. So now that we've taken some time talking about how to solve exponential equations, let's talk about how to solve a logarithmic equation. A logarithmic equation is an equation that involves a log expression with different variables. So similar to exponential, if there's a way for us to rewrite this, so we have log base some number that's the same on both sides, then we can say that the other two pieces must be equal. If log base 2 of x is equal to log base 2 of 7, in order for these to be exactly the same on both sides of the equation, x has to be equal to 7. What you see written down below is that sometimes it's easier to exponentiate both sides so we can see it in a form that we're more comfortable with, but it's really going to depend on the type of problem. So let's look at a variety of different types of logarithmic equations and talk about the best approach to solving them. So there's a couple of different styles of problems you might see. You might see a problem that only has one logarithm. You might see a problem that has two logarithms. You might see a problem that has a logarithm set equal to another logarithm. So if there is more than one logarithm on the same side, go ahead and condense using those properties that we learned in 6.5. It's going to make your life easier to not have to manipulate something that has two different logarithms. So if we look at example C here, we have two log bases of 2, which means we could condense those. Since this is addition, we can condense them with multiplication. If there's only one log, like there is now, then we can switch to exponential form. So we can say 2 to the power of log base 2 of 5x equals 2 to the power of 4. Or we can simply just switch form. So I'm going to do it 2 to the log base 2. And 2 to the 4th. So we're exponentiating both sides. We learned a property that says that 2 to the log base 2 is 1, so we're left with 5x. So this is going to be 5x equals 2 to the 4th is 16. And then if we divide both sides by 5, we get that x is 16 over 5. And we could plug that back in to confirm. I'm actually going to plug it back into that green step, log base 2 of 5 times 16 over 5. So log base 2 of 16, what exponent takes us from 2 to 16? It's 4, and that's what we were supposed to get. So if you have two logs, you can condense them, then you only have one. Then you can exponentiate both sides or switch forms, and then you can solve and check your answer. It's really important to check your final answer because we have domain restrictions with logarithms. We're not allowed to put a negative number or to take the log of something that's negative. So we need to make sure when we get our final answer that when we plug that back in, we don't end up with a negative number. And again, this is because logs and exponentials have different domains. Now let's look at example D. We have two natural logarithms, but we have one on each side of the equation and there's nothing else going on. What the property that we just looked at before says, if we have log of something equals log of something, we can set those two inside parts equal to each other. So since both of these are natural log of something equals natural log of something, in order for this to be true, they have to be the same. So we can simply set x plus 9 equal to 3x minus 5, and then we can solve for x. So I'm going to subtract 3x on both sides, negative 2x, and subtract 9 on both sides is negative 14. So x is equal to positive 7. And I'm going to check and make sure that that works. Natural log of 7 plus 9 is going to be 16, natural log of 16. Natural log of 3 times 7 minus 5 is going to be also natural log of 16. So what we have is correct. The reason we're allowed to just set the two inside pieces equal to each other, I'm going to show you the why, even though you don't need to show this step, is what I'm really doing is I'm exponentiating both sides. I'm saying e to the power of natural log of x plus 9 and e to the natural log of 3x minus 5. The e in the natural log are inverse operations, so they undo each other, so that's how we get to this step that we started at before. So let's look at some more examples and identify the best strategy and approach to take and work through them together. Okay, if we look at number 5, there's one logarithm, one natural log on each side. So what did we just do in the last example like this? What we did was we set these two pieces equal to each other and then we solved. So go ahead and do that. Set 4x minus 7 equal to x plus 5 and go ahead and solve. Now remember, we need to check our answer at the end. So I'm getting that my answer is x equals 4, but let's check. The most important thing we're really checking for is that whatever number we get, when we plug it back in, we don't get a negative inside the logarithm because that is outside the domain. We're not allowed to actually put negative numbers in there. We're not allowed to take the natural log of a negative number. So I'm just going to check what happens if I plug in 4 to the left side. 4 times 4 is 16. 16 minus 7 is 9. And on the other side, 4 plus 5 is 9. So we are good to go there. Now on number 6, there's only one log. So we can exponentiate both sides. We can say 2 to the power of both sides, or we can think about that in the same way as switching forms. So I'm going to write 2 to the log base 2 of 5x minus 17 equals 2 to the power of 3. But again, you could also just switch forms. It's going to get you to this next step. Since 2 to the log base 2 is 1 and 2 to the third is 8, this is going to give us 5x is 25, which means that x is 5. And then we're going to go ahead and check our answer. 5 times 5 is 25 minus 17. This is log base 2 of 8. 2 to the what power is 8? 2 to the third power. So we are good to go. All right, I'm going to put up 2 more problems, and I'm going to have you work through those 2 on your own, very similar to what we just did in 5 and 6. All right, go ahead and try numbers 7 and 8 on your own. Don't forget to check your answer. Then unpause the video and see how you did. So hopefully you had time to try these on your own. On number 7, we have a log on each side, so we can set them equal to each other, and then we can solve for x. We're going to get that x is equal to 2, and then we're going to go ahead and check our answer. Natural log of 5 times 2 is 10 plus 2 is 12, so natural log of 12, and then on the right side, 2 plus 10 is 12, so we are good to go. On number 8, since there's only one log, we're going to exponentiate both sides, so 3 to the log base 3 of 10x minus 9 equals 3 to the power of 4. Since 3 to the log base 3 is 1, we're going to have 10x minus 9, 3 to the fourth is 81, and then go ahead and solve that equation for x and check your answer. And that one works as well. So let's go ahead and look at 2 more solving examples that are a little bit more complicated and work through the first one together, and then I'll have you try the last one on your own. All right, on number 9, we have 2 logs that are on the same side. So what we're going to do first is we're going to condense. So the operation that's happening with these 2 logs that are both base 10 is addition, so I can condense that with multiplication. And then I'm going to go ahead and actually multiply those out. So this is going to be 2x squared minus 10x. Now that I've condensed, there's only one log. So I'm going to exponentiate both sides, or I'm going to switch forms. Remember, there's an invisible little 10 down here. If there's no subscript written with log, that means it's the common log, which means it's base 10. So if I exponentiate both sides, I'm going to get that 2x squared minus 10x is equal to 100. And then I'm going to get everything on the same side, so I'm going to subtract 100 on both sides. And now I have a quadratic that I need to solve. Before I solve this quadratic, I'm going to divide everything by 2 so that I get to factor with smaller numbers, or I get to try to factor at least with smaller numbers. And this does, in fact, look like it's going to factor x minus 10, x plus 5. So now we're going to end up with 2 solutions, negative 5 and positive 10. Now here again is why it's essential to check our answer. We are not allowed to take the log of something that's negative. So I need to make sure that when I plug these in, I don't ever get a log that's negative. So let's start with x equals negative 5. That's going to give me log base 10 of 2 times negative 5, 2 times negative 5, that's not going to work. So x equals negative 5 is not going to work because I'm going to have a negative inside my first logarithm and inside my second. So now I'm going to check x equals 10, log base 10 of 2 times 10, which is 20, plus log base 10 of 10 minus 5, which is 5. We have positive numbers here. These can simplify with multiplication, and this is going to work out nicely. So the only solution is going to be x equals 10. Again, we need to make sure that whatever answers we get when we plug them back in, we don't have the log of something negative. Go ahead and try number 10 on your own, and then unpause the video and see how you did. All right, so first I condensed, which means I'm going to multiply 6x times x minus 1. That's going to give me 6x squared minus 6. Then we're exponentiating both sides, or we're changing forms, which is going to get us to 6x squared minus 6x equals 36. I chose to move 36 over and divide all the terms by 6, so I got to work with much smaller numbers, which made it easier to factor. Now I have my two solutions that x is equal to 3 or x is equal to negative 2. So again, I'm going to check. If x is equal to negative 2, then I'm going to have log base 6 of negative 12. I don't even need to keep going. This is not going to work. Negative 2 is going to be an extraneous solution. Remember, an extraneous solution is a solution that doesn't work when we plug it back in. And again, those are created because of inconsistencies in the domains of the two functions that we're talking about here, logs and exponentials. If x equals 3, then I get log base 6 of 6 times 3 is 18. Plus log base 6 of 3 minus 1 is 2. If I condense this, that's going to give me log base 6 of 36. And 6 to what power is 36? 6 to the second power. So our only solution is going to be x equals 3. Now, I never like to miss a chance for us to talk about transformation. So the very last thing we're just really briefly going to do is talk about what does it look like to transform a logarithm function. So just like always, our horizontal things are happening inside and they're the inverse of what we think. But where is inside with a logarithmic function? Inside actually means we have log and then we have parentheses indicating that something is happening inside. So in purple, you're going to see all of the things that are happening horizontally. They're happening inside parentheses connected to the log. As opposed to all the things that are happening vertically, they're happening outside of the log portion. So go ahead and pause the video and try and work through number 11 on your own. Again, this is not anything different than we have done in previous sections. We're just using the same knowledge on logarithmic functions. Then unpause the video and see how you did. All right, hopefully you had time to work through that. Let the graph of g be a translation 2 units to the left. So g of x, 2 units to the left is going to mean inside we're doing x plus 2. And 5 up. Plus 5, followed by, now I need to figure out whether or not there's an issue with order, followed by a vertical stretch by a scale factor of 3. So the order is wrong here because we're supposed to vertically stretch before we translate up and down. Because the order is wrong, I'm going to add that extra set of parentheses and I'm going to put the 3 in front. Now, remember, x plus 2 is going to get substituted into x in the original function. So g of x is equal to 3. Now, instead of f of x plus 2, I'm going to say log base 7. So log base 7 of x plus 2 plus 5. And now I'm going to deal with that stretch. So I'm going to get a 3 that's going to go in front of this log base 7. And this 5 is going to become a 15. So g of x is going to be 3 times log base 7 of x plus 2 plus 15. So we covered a lot of interesting topics in this lesson. We talked about how to solve an exponential and how to solve a logarithmic equation and how to check for extraneous solutions. We talked about different strategies based on the way that the problem is set up. And hopefully now we can approach a problem by deciding that best first step and working through it in a logical fashion. And then at the end, always checking for extraneous solutions, making sure that the answers that we're saying are the final answers do in fact work in the original problem. Lastly, we just recapped transformations and talked about what does that look like with a logarithmic function. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.